Hydrogen is going to play a key role in our fight against climate change, but it's essential that the hydrogen we use has no associated greenhouse gas emissions. Here at the University of Exeter, our research focus is in green hydrogen production, which, unlike the vast majority of hydrogen produced today, has no reliance on fossil fuels. Over the past few years, we've made some really great progress in the area of renewable energy generation. More and more of the energy that we consume comes from solar or wind. One of the main obstacles that we're yet to overcome is cheap and reliable energy storage. This is really important because the sun doesn't always shine, the wind doesn't always blow. We need to be able to save up energy from times when renewable energy generation is in excess, and then release it at a time of our choosing when power isn't as available. Our research focus is mainly electrochemical energy storage, so things such as redox flow batteries, lithium-ion batteries. But some of the most interesting research that we're doing is in green hydrogen production, using a process known as electrolysis. With this, we can split water molecules using electricity. The energy that's contained within this hydrogen can then be released at a time of our choosing, and the great thing is that there are no related greenhouse gas emissions with this. The only byproduct is water. This is unlike every other method we have, which will rely on the extraction and processing of fossil fuels. There are several different types of electrolyser that we can use to split water. The specific type that we're working on here at the University of Exeter aims to combine the advantages of many of the other types while negating their disadvantages. This means that we're able to use cheap and abundant materials to produce high purity hydrogen in a very efficient way. The electrolyser cell contains two electrodes, the anode and the cathode. Each of these electrodes incorporates a catalyst made up of cheap and abundant materials such as first-row transition metals. Sandwiched between the electrodes is the anion exchange membrane, or AEM. This allows negatively charged ions to pass through while restricting the passage of positively charged ions. These three components make up the membrane electrode assembly, or MEA, which is an integral part of the electrolyser cell. Either side of the membrane electrode assembly are the gas diffusion layers, or GDLs. These allow the gases that are generated at the electrodes to diffuse away, ensuring that there are always sites available at the electrodes to produce more gas. On the outside of the gas diffusion layers are the current collectors, which enable electric current to pass through the cell. Water is pumped into the cell on the anode side and passes through the membrane to the cathode side of the MEA. When a voltage is applied to the cell, electrons flow to the cathode in the form of electric current. The electrons react with the water molecules at the cathode, reducing them to hydroxide ions and molecular hydrogen. This is known as the hydrogen evolution reaction, or HER. The negatively charged hydroxide ions migrate through the anion exchange membrane to the anode, where they undergo multiple reactions to produce molecular oxygen, water, and electrons. This is known as the oxygen evolution reaction, or OER. The electrons pass to the current collector and flow out of the cell, completing the electrical circuit. The water and oxygen are pumped out of the anode side of the cell, while on the cathode side, pure pressurized hydrogen gas is extracted.
Hydrogen for me is simply fascinating. Hydrogen makes up 3/4 of the mass of the whole universe. In 1950s and 60s, GE and NASA invented the proton exchange membrane, PEM water electrolyzer. This device was originally proposed to be used for space station applications. Since then, PEM water electrolyzer and fuel cell technology have been developed into very matured technology and well commercialized. We have found that there is a cost issue towards practical application of hydrogen in terms of PEM and fuel cells, because they need expensive membrane to be operated in acidic media, and because they are too dependent on the use of precious metals as a catalyst.
The catalyst will greatly improve the overall performance of the electrolyzer, which is the key point for the employment of green hydrogen production.
At the University of Exeter, our research focus is to develop anion exchange membrane, which we call AEM. Compared to PEM system, AEM cell is capable to utilize cheaper non-precious metals. Therefore, we can reduce the cost significantly.
I believe green hydrogen will become the perfect candidate for the replacement of fossil fuels, which is friendly to the environment and is good for us to get a cleaner, better future.
If comparing with PEM, research effort and funding towards AEM technology looks significantly small. I would think we need to put more effort towards this research field because AEM technology combined with renewable generated electricity is capable to produce green hydrogen at low cost. I would say what I'm saying here is only the tip of the iceberg of hydrogen technology. There are still huge amounts waiting for us to explore. Thank you.